My name is Paulius Velesko. I am an application engineer at Intel, but I actually work on-site at Argonne, so it's my kind of a daily mission to help scientists and engineers optimize their code. So mostly deal with code optimization and porting to different architectures, and I will tell you about the Intel tools that I use to do that. So first, if you want to do something with Vtune, which I highly recommend, you should download a local copy to your machine. So I put, you can just Google it, or you can go to this directory and get the actual installation files. So if you're going to do the hands-on later, you're going to need to have that. So there's a Windows, Linux, and a Mac version along with a license file there. So go check that out. So intro, I'm pretty sure all the previous speakers already covered this, but we have the way we get performance is through parallelism, and we have different levels of parallelism on these big systems. We have parallelism with a core, within a core through SIMD parallelism, and that's, you get that performance using vectorization. You have parallelism within a socket because each chip has multiple cores, and we take advantage of that using threading. And we have node and cluster level parallelism, and that's mostly MPI. And we have different tools for profiling and optimizing at each of those parallelism levels. So before I get into more serious tools, I want to mention compiler reports. And you see I say free performance metrics. Who doesn't like free? They're free because you don't have to do anything to get this other than add a line to your compilation line. You do that, recompile your application, and for every object file that you compile, Intel compiler will spit out an optimization report, which will give you all of this useful information. But I think most importantly that it tells you is vectorization, right? So I'm a terrible programmer, so every single time I do something, I tend to break things. And if you run your app, you recompile, you run your application, and then ends up running way too long, that result is not very useful to you because you broke vectorization and you only noticed that after you submitted your job. You waited in the queue, it compiled, it ran, and then you see that everything's slow. So I think it's good practice to have something like this. And if you're working on a part of the code that is performance critical, you should be semi-regularly checking your optimization report to make sure that the things that are supposed to be vectorized are still getting vectorized, and to the appropriate vector length. And like I said, there's other stuff there that you can look at. I'll leave this as an exercise to the reader. So the first thing that's part of Vtune, not exactly Vtune, but it's called application performance snapshot. So this is a relatively new tool, and it gives you a good starting point in terms of understanding the performance of your application. So it's a lightweight tool. It has very low overhead and it's scalable. So if you get a code that you haven't worked with much before, you don't know what's going on in terms of performance, you can use APS to get a rough idea, right? So it's very easy to use. You don't need to have anything installed on your local machine. You don't need X forwarding or anything like that. You run this tool, it generates an HTML file, and then you can download it to your local machine and look at it. So the way you would do that on Theta is, so first, very important, run out of projects. Don't run out of home. And if you try to run out of home, it will fail. It will tell you something about file system or not tell you anything at all. So make sure you run out of projects. And then the default Intel module on Theta is Intel 2018. So you want to swap that for Intel 2019 Update 3. That's shown there. That module will load the 2019 Parallel Studio with a compiler and Vtune, Advisor, and APS. So that will have everything that you need. And then in order to actually run APS, all you do is you do what you do normally on Theta, except you add APS before the name of the executable. It will run, it will be super fast, and then it will tell you, hey, I'm done now, do APS-report and the name of the directory that you need to apply. And once you do that, you're going to get an HTML file. You download that file to your laptop, and then it looks like that. So I think this is neat, but I'm the kind of person that would find something like that neat. It tells you the overall application time. It tells you, it breaks it down. It tells you a flop estimate. It tells you the CPI. It tells you a little bit about MPI, OpenMP, memory footprint, I/O, memory, stall issues, and even vectorization, right? I think most importantly, it tells you that your application is MPI bound, so kind of like you have a good rough estimate on how your application performs as a whole and where to look next in terms of getting performance. So once if you already profile your application before with different tools, you can skip APS. But then after that, you really want to drill down into your code and figure out exactly which parts of your code need optimization. So within a cluster level, there's other tools that are better suited for running on Cray systems. So use Cray profilers as opposed for Cray MPI, because there's an Intel trace analyzer for analyzing MPI, but since this is not an Intel MPI system, don't use that. So I will only focus on Vtune for this presentation. Yeah, you should check that link out. There's a guide on the ALCF website that mentions a lot of the basic stuff about Vtune. I'll refer to this later. Yeah, so Vtune is a profiler. It has low overhead and it's accurate and tells you a whole lot of things about performance. I think it has two sampling modes: user space sampling and event-based sampling. So the user space sampling is essentially just keeps track of how long things are taking, but it doesn't tell you anything related to hardware counters. So I don't like that mode that much. I really like the event-based sampling. Vtune does a lot of things, but it cannot do all those things at the same time. So we have these predefined collections that are part of Vtune. And you can think of these predefined collections as sets of features that are either enabled or disabled. So the best one, the one I use the most, is Microarchitecture Exploration. So that's the one that uses event-based sampling, and you run that and multiplexes in time all the events, so you get a good estimate of all your performance counters. Yeah, so that's the one I use the most because there's no other Intel tool that will give you that level of detailed information. The stuff that we have outlined here in light blue, we have Python support, and what that means, I'll come back to this later. So getting your application ready, this is what you have to do. So it's not a whole lot. I think it's been mentioned in previous talks. So, and it's for the same reasons: -G for debug symbols and dynamic for swapping out the runtime libraries, especially OpenMP1. So running Vtune on Theta is a little bit different than running it on other non-Cray systems, and that's mostly because of the Cray MPI. use AP run instead of MPI run, so that changes things a little bit. At this point, I think it's important to mention that Vtune is not the tool that you run at scale, right? So you don't want to profile 1 billion ranks and 1 million threads. That's too many. I think the overhead costs scale, pretty sharply with the number of resources that you're using on overall system. So for this reason, you normally want to profile the minimum amount of threads that's reasonable, that's representative of your application, and you want to profile 1 or 2 ranks. And most of the time that's totally fine because every rank is doing pretty much the same thing in terms of computation. And there's these other things that you have to take care of in order to get profiling to work on Theta, but for that reason we have a script we have a template script that will help you with that. So if you wanna get started with Vtune, you can Google Vtune on ALCF. That should show up as a first result. And that is where we have some basic information, a little bit of a guide. We have the example script on the website, but we also have the same example script on /soft perf tools Intel Vtune, so you can go to either. But this script is great. It tells you, it allows you, it does all the MPI kind of setup, the size of your job, nodes, the queues. Then it does this very important thing, which allows you to profile. It attaches to a single rank as opposed to attaching to all of the ranks. And it's kind of cumbersome to do it without the script. It takes a binary as an input. So if you want to get started, you have a executable that's compiled with -G and dynamic, and you're in projects. You just copy the script. You might have to change something inside the script, but most of the time you don't. And then you can just submit the script with the name of your executable and maybe even an input file if that's how applications run normally. And then another thing is important, that Vtune needs to know the location of the source files. Otherwise, it will not be able to show you. Say you click on a function, it will not be able to pop up the source file for that function. So that's also useful. And it timestamps the result directory. So it creates a result directory it's named after your application, your input file, and the time. And I think that's kind of important because I tend to delete things and then I need them and I have to rerun jobs. So I think it's neat. Also saves the Cobalt file, so you know exactly how you ran your application, all the parameters and stuff like that. So I mentioned that you might want to customize this, right? So in order to do that, you can say you want to change a collection, or say you want to customize one of the predefined collections that we had earlier, right? So you can do that. Either go to the ALCF website, go to the Intel website, use the ampleXC-cl-h, right? The command line help menu, or, and this is how I got started actually, if you use the GUI, you can collect results through the GUI as well. If you're collecting, say, on your local laptop, local machine, the GUI shows all the options that are available, and you can, tick things on and off, because sometimes you don't know that, there's a feature out there that you might be interested in. But then the cool thing is that on the bottom right, there's that command line button. If you click that, it will tell you exactly the equivalent for the command line option that you might want to, you can just copy that and insert it into your Cobalt job. So say you did that. You submitted your job. This is how you would submit it, right? And for the simplest analysis, you can do hotspots. You get dropped down into this result. And this result just tells you yet again, elapsed time. It will tell you a little bit about, spin time, how effectively you're using your threads. This is a histogram of how many threads you're using overall, and you can see that, big thing around 0. That's because this application is not using threads very effectively, right? So if you then go to bottom-up view, you get to the main window, I'd say, of Vtune. And so here, first, you'll see, I guess, this top bracket up top, right? That is an OpenMP region, right? You can, if you hover over it, it will tell you the name of the region, the location of the region, right? And in this region, all these threads become active, and you see the red stuff, they're just spinning because they're not actually doing any work yet. So this could be kind of like a big outer parallel, OMP parallel region. And once we get into, you see this dark brown stuff, that's where the OMP threads are actually doing useful work. So for this particular example, you'll see that threads are not being used very effectively because there's essentially just not enough work for all of the threads to do. So this is another result that I have, and I think the best thing about Vtune is that it gives you a lot of flexibility in how it presents and groups the information. So, for example, this is where I get started. If I right-click on CPU time, I can put, instead of showing all my time in seconds, I can show it in % of overall time, which to me most of the time is much more useful. Then you'll see that in this particular example, there's this function AA, right? It shows up twice. So this is a bottom-up view, right? So if you look at your application, as a tree, once you enter main, that's kind of the trunk. And as your execution flows, you get all the way to the leaves. So these are all the leaf nodes, right? And the reason why AA shows up twice is because in this particular application, it was called from 2 different places. So the call stack for them is different, so that's why it gets shown up twice. But I can change that. I can group this by function source, right? And since they both have the same source, they get aggregated into one. And now you can see that actually one function takes 14% of the overall execution time. Another thing is here you'll see that right now it says show inline functions. There might be a case that you don't want to see functions that were inlined. You want to see kind of like a last function call that was, we actually did a jump, right? So if you selected to hide inline functions, you'll see that AA was actually just a function that was inlined into a bigger call. In this case, now we have the single call that takes more than 1/4 of the overall application time, and if you click on it, it will actually take you to the source for that function as well. And then right now we're showing functions only. Sometimes you want to see functions, sometimes you want to see loops. A lot of times loops are optimization targets, right? Because loops take a long time. So for example, say you're working on a loop that is very expensive in your application, right? And you decide that you want to vectorize it, and you vectorize it, and now you're curious, how did that vectorization affect my overall application performance, right? So you can change this view to show information for loops only. So this can also be quite useful. So I mentioned that bottom-up tree, right? So top-down, bottom-up, they're inverses of each other. So if you go to a top-down tree, you'll see that it's the same thing, except now it's at the bottom of this call stack. So sometimes for applications that I don't understand really well, I tend to prefer a top-down view because, I start at main and then I have to, drill deeper into code until I figure out what's going on, right? So top-down view is quite useful. Then you'll see this little button there. That changes the views of your application, right? So remember all those predefined collections? I said that each collection is like a set of features that are enabled or disabled. So these sets can somewhat overlap, right? So if I do, for example, HPC performance characterization, right, that will essentially, the information that's collected in that includes all the information necessary to display basic hotspots. If I collect basic hotspots, I still get HPC performance characterization view, but if I drop down into it, it's not going to show all the information that's available in like a native HPC performance characterization run, right? Because there's less information that's collected using basic hotspots. So the views will depend. Now this is another example. You'll see that this is now a microarchitecture exploration view. And like I said, the views, what you see on the GUI will vary depending on which collection that you do. This result in particular, you'll see that I have my L1, L2, and like TLB misses, all that stuff. So what you see here, these metrics will also depend on which architecture you collect your result on. So this is collected on KNL. KNL doesn't have as many performance counters as, for example, Skylake, right? So if you ran the same result on a Skylake, you'll see a whole lot more performance counters. So that's something actually it took me a while to figure out. You'll see the timeline again. You'll see that some of the threads are not doing anything, so that's something to look into. You'll also notice that the timeline starts paused, right? So sometimes you might be interested in profiling an entire application, or maybe profiling just the first 10 seconds, or maybe you want to skip, maybe you have like a very long setup that you're not interested in profiling at all, right? Because that's, say at production, the setup doesn't really take that long compared to the overall execution. So you can start paused using command line, or you can end after a certain time, or alternatively, you can also instrument your code using this. So there's this ITT notify library that you can insert some instrumentation calls into your application and then run it through Vtune, and based on those calls, it will start or stop collection. So if you're interested in like a very small part of your application, you can put in 2 calls, one before, one after, and it will only profile that small region, so which can also be quite neat. So I said I'm going to mention Python. So yeah, how do you optimize a Python application, right? So what makes a Python application go fast is if it doesn't actually run in Python. So it's kind of a, yeah, I know. So in order to optimize a Python application, right? So say you write something in Python, and then you want to make it fast, right? So then at that point, you try to use accelerated libraries in Python, such as NumPy, right? Sometimes the features are not available in any of these libraries, or you have like a custom layer, that you really need to do something crazy. So you can write a C function and then call that C function from Python, and then that will be really fast. So what our Python support means is that if you run those analyses that were in light blue, it will use user space sampling, and it will preserve the Python call stack. So if you use any of the other ones, it will not preserve the native Python call stack. So the application will look like, oh, I'm entering Python, and then whatever happens inside of Python layer, I don't really know. It's kind of all aggregated into one, right? So to use Vtune, it's pretty much the same thing. You just do basic hotspots. You run your actual application as Python, and then your Python script and whatever arguments as a source. And when you do that, this is what you get, is that you can see this. You can't see, but you'll see that this is actually, these calls are happening inside the Python layer, and you can go into the call stack of your actual Python application and figure out which functions and which source files are taking a long time. And then on top of that, what you can also get is this thing on the right where you see the source code, and you can see the time taken line by line. So then you find this one line that's, say, taking 50% of your overall application time. Might be surprising because Python's kind of difficult with what it does. So you can replace that call with NumPy, or maybe this is the case where you have to write something custom in C. So then you're not going to be going out and optimizing NumPy. So once you get there, you're good most of the time. But you might be interested in optimizing that custom C layer that you have, right? But the performance of that C layer depends on the data that you run through it. So if your driver application is Python, you're still going to have to run Python, because Python is going to be feeding all the data into that C layer. So say you did basic hotspots, you found a region of interest, you replace that region with interest with some custom C call, and then you still see that C call is taking a long time, right? So then you can, then you know that you want to profile the actual native C layer, and then you can rerun your application using like microarchitecture exploration, and you can get performance counters for that C layer itself. So you can still use Python to drive your application and feed the data, and use Vtune for profiling the C. So yeah, -G, dynamic, run out of projects, and then some resources for you to look at. And there's going to be a little demonstration after this later. So if you have any questions this time.
So in one of the slides where you were showing hotspots by CPU utilization, you had performance attribution back to the loop level. Does that work only with the Intel compiler, or are you actually looking at the binaries?
I think it works with any compiler.